It was basically a bottom-up strategy where we took different industry, parameters like industry. Industry was again divided into cement, iron and steel, aluminum, textiles, pulp and paper, chloralkali. So these were the industries which were made bottom-up. Then there was transportation, which included road, then airways, then commercial transportation, buildings, how actually buildings consumption will change over the years. Due to net zero, the biggest problem will be coming in buildings. The cooling loads, which presently are one of the highest in the building loads, will increase by around 40 to 45% because of the climate change. Then we have agriculture, which is nearly constant. Then cooking. So cooking, I'll talk about it in the mission life interventions, data centers and electrolyzers. Now, when we are actually looking at something which is 50 years beyond, how to draft that net zero roadmap? We have to look historical data, and we have also to look at what are the technologies which are upcoming. So looking at historical data, we actually saw at 8 to 10 countries how actually they have grown over the years. So if we look at China, in 1998, it was at nearly the same place where we are today. So it was around 4 trillion economy. Its industry contribution was somewhere around 30%. So now we started thinking that from 4 trillion economy to that 20 trillion economy, near 17 to 20 trillion economy that it is today, we are also envisioning something same. So we are also envisioning that by 2047, we'll be reaching at a similar place where China is near today, or it will be in few years. So the growth will be in a similar pattern. How actually infrastructure will grow, how the transportation will grow, these all things will actually mimic. So we actually looked into that. So till 2047, we have actually grown India in a similar format. That is the growth plan of China since 1998. So around 25 years, and we are reaching somewhere around 2047 to that Viksit Bharat model. Then we started thinking, is it the same? Will it be the same thing, or we have to actually do some interventions in that? The point is basically you have to get the technology. We have to improve the technologies which are there today, like cement to steel ratio, which was there in 98. That isn't at present. So we have to actually change that technologies for today, but you have to take the growth path of China. And after 47, what will happen? If we actually reach that 12,500 per capita economy, then we'll start actually moving as the developed countries grow. So we have to actually shift our focus from there. Now, how life interventions can help here? See, we can't actually give the whole load of net zero transition to supply side. We also have to look at the demand side. We have to look at frugal mindset of consumption. We have to look at transition of transportation from normal private to a public transport level. So till actually we don't reduce the demand side, it will be very difficult for supply side to transition completely to net zero. That was the thought behind it. That's why we have also looked into we'll talk about it in a few slides ahead. So here actually is the first thing where net zero, life interventions help. If you look, at many of these net zero pathways, they will show you demand side grow by around 3 to 4 times. Then it becomes unrealistic for us to draft a supply side roadmap, because if then the solar and wind will start growing towards 4,000 to 5,000 gigawatts, which is not possible because of the infrastructural issues. We don't have the demographics to cater that supply demand. So here we actually looked at how life intervention can help you in reducing your demand side. If we see, we have unrestricted demand to industry area because we want to grow as a manufacturing country. But we actually reduced the transportation as well as the demand from buildings area. How did we do that? Transportation we reduced because we are, as per our roadmap, we are transitioning 100% or near 100%, around 95% to electric vehicles and around 70 to 75% to public transport. Unless we are doing that, the demand side grows to such a huge levels that it will not be possible for any supply side to cater that. Then agriculture is nearly the same because with all the technological improvements, agriculture efficiency will actually improve. Data centers is one thing where we had to break our minds because we don't have a data that how data center is going to grow. But still we gave it around 10% of the supply. So data center was one thing where this, what we say, roadmap, I'm still not very, what we say, confident about. The rest of the supply demand side was actually taken from, what we say, tested formula. Next we go to how this demand of 1200 MTOE that we are actually looking at in 2070 will be catered. So today, electricity caters around 18 to 20% of India's energy demand. But as per our roadmap, it will be catering somewhere around 75%. Out of that 75%, 55% will be directly through the grid, whereas 20% will be through green hydrogen. So green hydrogen will be playing a big part when we have to cater this demand. Green hydrogen will be helping in transition of hard-to-abate sectors like steel, a little bit of cement, and the transportation, especially the freight transportation, will be catered by your green hydrogen. So electricity will be playing a big part. Solar will be taking a lion's share. Nuclear is actually going to grow. So if you see the recent what we say roadmap for India in the budget session, so nuclear is expected to grow to around 100 gigawatts by 2047 and maybe 150 to 200 by 2070. The roadmap is not yet very clear, but at least till 2047, the vision is for around 100 gigawatts of nuclear. Then we come to emissions. So India's emissions are growing quite fast. So it was around 2,500 million tons or 2.5 billion tons in 2023, touching around 3 very soon. As per our, what we say, projections, these emissions are going to peak somewhere around 2040 to 2045. If we go from business as usual scenario, so we have taken actually two scenarios. One was a net zero scenario, another was a business as usual scenario. In that, it is peaking somewhere around 2050. So we can safely say that we should be peaking somewhere between 2040 to 2050, and we will be having a time of around 25 years to transition after that peak. Energy efficiency and life initiatives will play actually a big part when we actually transition from that zone to 2070, basically after the peaking zone. Now comes the biggest part. Okay, all said and done. This was very easy that actually we can grow our infrastructure, we can actually supply the demand, but what's the problem? What's the point that we have to look at? So it is the investment. So when we looked at what will be different phases of investment that we will be doing, it came out of around 13 to 15 trillion dollars. So 13 to 15 trillion dollars will be needed if we actually want to achieve this roadmap. We want to put new solar, new nuclear, new wind, new offshore wind, create infrastructure for electric vehicles, create infrastructure for hydrogen transportation. So these all will actually take 13 to 15 trillion dollars with a major share of 20 to 25% in generation and 35 to 40% in transportation. This transportation includes two parts. One was EV infrastructure, second is hydrogen infrastructure. So these two will be actually taking a big share. In generation also, basically the solar part will be taking 70 to 80% of this share. Next comes your transmission and distribution. Now think about a grid. So we are having one of the, we are the third biggest consumers of electricity after only China and USA. So when we are actually thinking that we will be putting around 60 to 70% of variable renewable energy into such a big grid, how should our TND be? It will have to be overhauled completely. The smart grids will have to be made, so around 12 to 15% of these 13 to 15 trillion dollars will actually be going into that transmission and distribution. And then comes your industrial and green steel infra. So you have to shift from the present boilers, the furnaces, to green steel infra. Now this takes around 1 to 2% of our GDP per year for next 50 years. And basically it is starting heavy. So you have to invest a lot during the next 20 years Slowly after that, this investment actually come down. So the major thinking should be basically that how these investments will be coming in the country. Carbon credits could be one way. I'll be taking you to the end of it in the next slide. So what should be the critical focus areas? Now these are very good numbers. Many of you will be thinking, okay, these are few numbers and I get these type of numbers from everywhere. So there are more than 7 to 8 agencies who are doing net zero, who are projecting net zero roadmap. But the point is, does these numbers matter? So anything which is happening in 2047, we are saying 100 gigawatts of nuclear, we are saying something around maybe 5 million, something about green hydrogen. The point is, when we do these projections, it's not that we want to give some funny numbers for 2047 or for 2070. The point is what is to be done today. So all these things are just the end of a tunnel, but the whole thing starts that where we are going to start now. So we have to look at both sides. As I told as I actually started my presentation with, that supply side alone cannot do net zero transition. Net zero transition will be done by both sides, demand side as well as the supply side. So what are the things to be changed in demand side? Sectoral mandates for emission reduction. So you may see very soon that there may be sectoral mandates for maybe refineries, for maybe fertilizers, that they may have to take green hydrogen. So we need a few off-takers for green hydrogen. Then VGF support, maybe in the form of CFD or maybe directly in the form of VGF, because there are many technologies which need some support. Introduction of carbon price, all the investment that has to come in, maybe carbon price will be helping in that. Efficient urban planning for transport energy demand optimization, that's a self-explanatory. Introduction of demand response and agricultural load shifting. Now think about it, when we were doing this roadmap projections, the biggest problem was storage. So how do we get that 2,000 gigawatts of storage in the country, which will actually expand in future? So the point is, can we shift that load to the solar zone? Because we will have an ample amount of solar. If we can shift that demand side to solar hours, then we can actually reduce some part of that storage. In supply side, resource reevaluation. So it's a log-mating thing. The government is actually working on that. So previously we used to say we have only 750 gigawatt of solar, but I think it will be reevaluated very soon. Then fast track capacity addition. That's actually you can see everywhere. So everybody is talking about fast track capacity addition. Indigenization of supply chain. This is one thing that if we are looking at a technology we know that we are going to invest huge in it, then it has to be indigenized. Technological interventions, preparing coal fleets for 1 to 2% ramp. So with such a huge variable loads, 1 to 2% ramp is actually required. And it has to be across the country. It's not just a few stations will be doing it. If only a few stations will be doing it, this 1 to 2% can go to 7 to 8% also. So it will become impossible for those stations to do something like that. And I'll end it with strengthening transmission grid and regional grid interconnection. This will be needed for catering load of a country like India. Thank you. That was my time.
Thank you, Nishant. Very good 360-degree overview you have given about how India can achieve net zero by 2070, and especially the building sector. You have mentioned very well. We need to decarbonize building sector as well as a first step. And now Mr. Sanjay Chetri, I think he'll be sharing his presentation on subsurface energy for space conditioning, I think which will include building sector decarbonization strategies as well. So yeah, over to you, Sanjay.
And if I were to include fuels such as diesel in there, then that comes to a figure of 76.1 million tons of oil equivalents. And out of that figure, 80% of that number is from the residential sector. You can see from the slide that the peak demand has also surged by 79% in a decade. So, as the world is moving towards carbon budgeting, as we are moving towards our net zero goal, we have to prioritize those sectors which can contribute to the economic development and GDP. And we need to deprioritize or decarbonize those sectors which we can do easily. And building is one of those. Because if we can decarbonize the cooling sector in the buildings, or the cooling segment of the buildings, we can decarbonize 40 to 60% of that energy. So 40 to 60% of 76 million tons of oil equivalent we can decarbonize. So today I'll be talking about the different approaches which we can take to decarbonize the cooling sector, and by using subsurface energy. So renewable energy will be using to decarbonize the cooling space. Primarily, there are three techniques, and before that, we need to understand that ground can act as a perennial source of energy. Beyond 3 to 4 meters below the ground surface, the temperature remains constant throughout the year. We can tap that energy and we can use that energy to cool our built environments. The techniques are using the earth air tunnels, where we can draw ambient air, pre-cool the ambient air, and then introduce it into the built environments. Another method is using direct ground cooling method, where we can have thermal fluid to exchange the heat between the built environment and the earth. And the third one is using earth sheltered buildings. Let's go into each one of them. Using earth tubes, we can have a network of tubes and pipes in the ground. We can draw ambient air. We can make them pass through the network of tubes and pipes, and then introduce into the built environment. So this is particularly suitable for buildings which have high requirement of ventilation, such as schools, offices, and hospitals. In the direct cooling approach, ground cooling, what we do is we have earth pits. We can either use air as a medium or thermal fluid to extract heat from the building and exchange it with the ground. So this is another source of renewable energy. We can have geothermal cooling ponds, where we can use nearby water bodies, to dissipate the heat which is accumulated in the built environment, and then exchange the energy. We can have partially or fully covered buildings which can use the thermal properties of earth and thermal mass properties of the earth to reduce the heat ingress in a building. Another method is using boreholes. We can have boreholes which are of 50 meter to 200 meter in depth. We can use thermal fluid to exchange the heat accumulated in the built environment and exchange it with the earth. So this is suitable in places where the water level is pretty high, because so that the exchange rate is better, the heat exchange rate. Using thermal mass properties of building envelope, such as thick concrete wall, can absorb the heat from the sun which is coming in, and store it and gently release it during nighttime, so that the heat gain in the built environment is less and there is a stable indoor environment. This is a very interesting approach of using night purging. So by night purging, what we meant is flushing out the heat which is accumulated in a building during daytime, and using the nighttime cool air to introduce it in the built environment. So at night, at around 3 a.m. to 6 a.m., the ambient air temperature is very cool. So if we can introduce that ambient air into the built space, then the heating load reduces significantly, and we can have an energy saving of around 30 to 40%. We all know solar assisted cooling, where we tap solar energy to help with our cooling needs. We have solar air conditioners, and we can also have other devices or equipment which can use solar energy to cool. And then ground source heat pumps. Basically, they use heat pumps to exchange heat between the built environment and ground source. So are they suitable for India? Yes, they are very much suitable for India. Earth tube systems, they are suitable for hot and dry regions, such as Rajasthan and Gujarat. So there are buildings in Rajasthan which are already adopting these technologies. So we can very well use them in our recommendation or in our consulting projects. Direct ground cooling, again, it's suitable. In urban areas like in Delhi, we have consequences such as urban heat island. So these kind of systems can reduce the urban heat island effects by using direct ground cooling. All we need is to dig earth pits, have thermal fluid in them, and use the perennial source of cooling. Geothermal cooling ponds, they are suitable to rural India where the water body is situated nearby. And earth-sheltered buildings, again, there are case examples in and around India where they are using earth-sheltered buildings. So why should we choose earth-based cooling? The first and foremost reason is they are renewable and sustainable source of energy. And as we are moving towards net zero 2070, we need to adopt every possible solution to decarbonize our various sectors, starting with HVAC system. By adopting the earth-based cooling system, the operational and embodied carbon and energy footprint reduces drastically, the environmental impact reduces drastically, and these solutions are reliable and they are feasible. There are vendors in the market who can install these systems for you. There are technologies in India who can use these kind of systems, so we should adopt these, definitely. Regarding the costing part, there is not much difference in the cost part. Of course, the earth-based cooling, they are a little expensive as of now in comparison to the conventional air conditioners, but if we consider the lifetime payback, the earth-based cooling systems are, the return is significantly high in comparison to the conventional air conditioning systems. As I told you, the environmental impact is very low and the maintenance is also very low. If I were to compare the life period of a simple conventional air conditioner, that is around 10 to 15 years, the life period of earth-based cooling systems can range from 10 to 25 years. So over these 25 years, you can get your return on investments. I would also like to talk about two real-world applications. One is an air tunnel system which has been installed in a hospital in Mathura. They are using air tunnel system for a 3-storied hospital, and they have already installed the cooling system of a capacity of 512 kilowatt hour, which is equivalent to 150 TR of cooling, approximately. Another one is earth shelter building. This spa and resort is coming in Rajasthan, and they have used the landscape to naturally cool their building, the built space environment. So by doing this, they are significantly reducing the energy consumption of the building, and which in turn reduces the carbon footprint of the building. So how should we go about this? So my recommendation would be awareness, because the technology is there, the vendors are there. I think what we lack as building owner is awareness about it. In India, how the buildings are being constructed is we normally hire laborers to build a building for us, because not many of us can afford professionals who are trained, who have the capacity to show us the right path. So we normally hire laborers. So maybe if us as building owner, we are aware of the earth cooling systems, we can tell whoever we hire that these kind of systems, or maybe we can hire those vendors who provide earth-based cooling systems. Policy support, some kind of policy support for passive measures is definitely required. We are already there. We have the building code in place. We have the green building certification systems. Maybe a little push on the passive measures can further decarbonize the building sector. So lastly, I would like to reiterate the fact that the earth-based cooling methods are cost-effective, sustainable, and definitely suitable for India. Thank you so much.
Yeah, thank you so much, Sanjay. I think you have given very good presentation on building cooling. So now I'll go to Vineet Bakshi, who is a director, business development, Lanza Tech. He'll be talking about waste to fuel and chemicals via novel gas fermentation technology utilizing microbes. Over to you, Vineet.
Thanks, Manoj, for the kind introduction. Session chair, fellow panelists, all the industry colleagues and captains out there. A very good morning to all of you. Past sessions and the presentation before me have been very engaging and very insightful. I hope the tempo continues throughout the day. And before I start my presentation, special thanks to organizers for putting up such a great event and giving us a chance to speak on the subject which is of much relevance today. So Lanzatech, it's a US-based company, and what we do is we are actually creating a post-pollution future, a future where there is no such thing as waste. Every waste is actually the raw material for products of daily use. And I'll be showing that how we are doing. And by doing so, we are actually kind of closing the loop and truly enabling the circular economy. So Nishant made my work easier when he discussed about the future scenarios. But just if you look at these scenarios, today we are close to 43 gigatons of carbon emission, and on the right side, it plots the temperature rise. And we all know why the fuss about net zero, because if we want to limit the temperature to less than 2 degrees Celsius, it has to be the net zero scenario. And when we talk about net zero, it's also very important to remember, that the carbon budget which was left as per last year, it was just 500 billion tons of carbon, which means cumulatively all the countries in the world, this is how much carbon which we can emit. And in case we want to limit that, so there are steps which needs to be taken. And how do we net zero? I think all of us know this. So these are imperatives on net zero. Pronounced use of renewable energy, energy efficiency, of course, the low-hanging fruits, use of biofuel, hydrogen, carbon capture and utilization. And again, the same thing. This is something which I took a screenshot from my phone 3 days back. World records the warmest January ever. And the way we are moving going forward, we'll keep hearing such things. We strongly believe that energy or power, especially the power, can be carbon free. We have renewables to take care of that. But when you talk about daily wear materials, it cannot be carbon free, because the carbon is very foundation of everything. I think it's in the products we use, the perfume you use, I think the clothes you wear, the equipments you carry in the planes, you fly via aviation fuel, the nature and the world, and I think it's in us, the clothes I'm wearing, this packaging material, everything's made of carbon. So what do we do, right? And for sure, the future will be, it's actually where our carbon comes from will define our future. And we at Lanzatech strongly believe that world already have enough carbon above the ground. We can, in simple 2 steps, we can just reduce the carbon emission, we can use and recycle that and power the circular economy. And that is something which we have been doing past 8 years in a plant in China, which was the first plant. We are using the steel mill waste gases emission, and through our novel gas fermentation technology, wherein we use a synthetic biology platform with the help of naturally existing microbes. We convert those emissions in single step to ethanol. And ethanol, as I'll be showing in subsequent slide, is the building material. Once you have ethanol, you dehydrate that, you get ethylene, you can go for any ethylene derivative products. From ethanol you have a pathway which is approved by ASTM, we call it the A to J pathway. And we also have a technology for that you can make. And then apart from that, what also, take a lot of pride in saying that 2023, like Lanza Tech was named by Times list of 100 most innovative company making extraordinary impacts throughout the world. And even more happy to say that 2024, our subsidiary company LanzaJet has been named in this Times list of 100 most influential company. So what do we do? How do we make it happen? Any waste gas, it could be your industrial gas from steel mill plants, your ferroalloy plants, your refinery fuel gas. We take that, we route it. In case the gas is pressurized, straight away we feed it to our reactors. In case it's not, we pressurize that. I think the magic happens in the reactor, which is our proprietary reactor. With the help of naturally existing microbes, in single step, we convert the carbon in the gas to ethanol. And the best part is, that there are certain processes which are not viable or possible through conventional thermochemical route. But once you go for a synthetic biology platform, something we have cracked and mastered, then you can make it happen. And in case you don't have a waste gas, a lot of MSW is there, you have agri waste, you can gasify that. The back-end process remains the same. You don't have that, you have CO2. I can use like pure CO2 along with hydrogen and then convert it into CO plus H2 gas, and then back-end again remains the same. I think the power of ethanol, as I said, is it's the basic building block. You dehydrate, we get ethylene. You can go into all kind of daily wear products, and I'll be showing in subsequent slide how we are doing that along with the partners throughout the world. So in a way, this is true circular economy where you are trying to keep the carbon locked within the ground. And how do we do that? This is a naturally existing microbes which was there. What we did at Lanza Tech is only, we identified that and kind of like re-engineered. Just some of the chemistry for those who might be interested. Since you have multiple sources of emission, so I've shown the different pathways in case you have a steel mill gas, what's the carbon efficiency and also what's the energy efficiency. And if you look at for all the waste gases, your refinery waste gas, or even you have a CO stream available, which going forward, like tomorrow, we'll be calling at the e-fuels. The carbon cycle is 100%. You have no CO2 when you see in the reaction on the right-hand side. And as I always say, the proof of pudding is actually in eating. So we are not just saying that something we'll do. This is something which is happening. We already have commercial reference plants. And if you look at the first plant which came up like 8 years back, other plants, they came up 2 years back. The plant is IOC, which is based on refinery first gas. That's the world's first 3G plant. The plant is getting stabilized. The right plant at Astral Mittal, it's a very big plant, and 64 KTPA corresponds to around 200 like TPD, which is a very big size compared to sustainable fuel standards. And the best part is if you look at, the plant, these plants are certified by ISCC Plus, and couple of the plants are also certified by RSB. Now RSB is the gold standards for sustainable products, which actually tells you the quality of the products you make in these plants. And so far, through our technology, clients have been able to abate more than 500 tons of CO2, and the combined capacity of ethanol production is around 300. And as I said, where others see waste, we actually see the raw material. So something of similar sorts can be done in India also. For last 12 years, we are running a plant based on MSW with Sekisui, based out of Japan. We started with the pilot plant, and then there was the pre-scale operation, and now a couple of months back, we signed a master licensing agreement with Sekisui. Throughout Japan, we'll be putting up decentralized facility wherein the MSW waste would actually be converted to ethanol. And very proud, 3 months back, NTPC signed an agreement wherein they have hired services of Jackson Greens for rendering EPC services, and they are using our technology for converting pure CO2 into ethanol. That's the first phase, and going forward, and Nishant, if I may take the liberty, the plans are to convert the ethanol to sustainable fuel, sustainable aviation fuel. And not just that, I think we all have furnaces in our existing assets. So something of those sorts we are doing in US. There's a project by the name of Project Secure, where from ethane cracker, along with Technip, our partner, we are capturing carbon, and then through gas fermentation, this has been converting to ethanol. And ethanol, as I said, is the building block. We are converting to sustainable ethylene. So the project is funded by US DOA, and close to 2 million of funding is for that. And the best part is, ethylene, the basic building block for any material, has a tremendous market value growth potential. And today, if you look at, you have done more than 370 ethylene crackers around the world. So this is like something which can easily be replicated everywhere. And why only ethane crackers? I think all the furnaces have CO2. So this can be done anywhere. Again, as I said, you have ethanol, the building block is there, you make ethylene, you can get to a long chain of material. There are plethora of opportunities which gets open for you. And I'll be focusing more like how we are doing. And this is something very interesting we are doing. I think all these things, we have an exhibition booth in stall number 2 in the US Pavilion. Please do come and see all of this. Like witness it yourself. I think all these products have actually been made through waste. I mean, just imagine you have steel plants or ferroalloy plants somewhere. The waste is being emitting. You capture the gases, and along with our partners, like we make ethanol, and then ethanol can be converted to ethylene oxide to MEG, and then you add the PTA to that. You get PET for making like close material, PET fibers, or for packaging. And this is all what we are doing. Along with Borealis, we gave them ethanol after MEG, and we gave them ethanol. They made from EVA. The shoes sole can be made. With Gucci, they came out with this campaign last year, wherein they showed entire perfume made out of recycled carbon. So this is something which is happening. It's no more a fantasy. It's happening, and we'll show you at a stall how this project looks. And another interesting thing is, when you talk about SAF, today like SAF is the buzzword. A lot of demand is there. Companies are coming out with policy throughout the globe. But in India also we have indicative targets, although these are not mandates as of now. And as Nishant said, we strongly feel that mandates should be there, for creation of a demand which actually enables and provides like fill-up to these things. So India also we have an indicative target of 1% by 2027, 2% 2028, and 5% by 2030. But the fallacy is, you actually don't have SAF anywhere around the world. Just the numbers, like how much of fossil ATF is being consumed, close to 100 billion, and compared to that, just 160 million of SAF is there. So a lot of opportunity, like whatever pathways you choose. Somendra is sitting over there, so they have a couple of pathways, like we have our own pathways, a lot of companies. But the fallacy is, something needs to be done. So we, at Lanza Tech, after mastering and coming out with commercial references for ethanol, 2018, we also developed the technology from ethanol to jet. We had transatlantic flights from Seattle to Orlando, and later we spun off a separate company by the name of Lanza Jet for funding purpose. And today, along with Lanza Tech, we are coming out with a solution which we call the circular. And why circular? Because it's an end-to-end solution from any waste solid, waste is gas, pure CO2. We make ethanol, and then we can make SAF. And the best part is the SAF which we make, it has the flexibility of 90-10 swing. You can make like 90% SAF and 10% renewable diesel. Both already have market. The country is struggling with respect to biodiesel blending. Renewable diesel can straight away go there. And if someone wants, we can also swing it other way, making like 75% of renewable diesel and 25% of SAF. And it is just SAF and renewable diesel, like no other projects like naphtha compared to us competitors. So that's the beauty. And going forward, this is not what we are saying, this is what ITA says, that you have a lot of potential of this technology if you use that. Yeah. The lady in red, that's a CEO, Dr. Jennifer Holmgren, and that's the flight I was talking about. And a lot of projects we are coming out across the globe. I'm glad to inform the first biggest SAF plant in India along with IOC is coming up based on our technology. And that's a 30 million gallon plant. And we also have our own 10 million gallon plant which is mechanically completed, and so we'll be commissioning that. And the only company to have so far a commercial plant based on ethanol to jet platform. And this is something interesting, we are not just stopping at ethanol, that's the first step. Going forward, we are working on different microbes. So from the same reactor, the same setup, just with the change of microbes, we'll be able to make isopropanol, ethanol, and more than 100 chemicals through synthetic biology platform. And last but not the least, this is something latest, utilizing CO2 to make protein. I mean, fetches a tremendous value, and this is something which we have been able to crack. So far, the protein have been approved for animal feed usage. The trials are going for human consumption. And the best part is, anybody like utilizing our technology, so this is the market value we give you. I mean, if you look at it in terms of ethanol, sustainable aviation fuel, the nutritional protein,
yeah, Vineet,
I think opens immense opportunity.
Yeah.
Thank
you so
Thanks.
much, Vineet.
Thanks.
Wonderful presentation. I think you have given very good insight, on how this greenhouse gas you are capturing and converting that, into some useful products. So it's a very insightful. Now I'll request Ms. Avi.
Thanks, Manoj. Hi, everyone. Good morning. My name is Abhiti Goyal. I'm part of Shell Technology Center, Bangalore. I've been working there for about 4 years, and the presentation that I'm going to share is co-authored with my line manager, Suranjan Sarkar, who is also in the room. Before I start, I need to go to the next slide. Yeah, it's a lot of fine print and basically says, please do not make any investment decision in Shell based on my talk today. You can decide independently, but I can't take any credit for it. That's what it basically says. Okay, back to India Gate. So what I did actually, listening to the talks last 2 days, I decided to remove a couple of slides from my introduction, because I guess all of you here, we're present here, and that itself sort of justifies any need to really tell you why energy transition is important, especially carbon reduction and maybe different solutions, including electrification that way. So the question of what we need to do is more or less clear. It's more on the how that we're struggling a bit, right? So that's the talk that I have, using 3 examples related to where Shell is interested in. I'd be trying to convince you to look at what we call a systems modeling approach for decarb pathways or roadmap generation. right? Don't worry about what system might mean here, what modeling contributes here, because that's the talk all about, and I'm going to talk you through it. Yeah, so you must have heard there are like multiple solutions, a lot of technologies that we can utilize in order to sort of strengthen our pathway to decarbonization, right? A few are there on the slide, but I'm sure like the presenters before me also mentioned a lot of different pathways, gas value chain from ethanol to ethylene to what we use in a daily life, or different pathways from electrification, either generating green renewables or using CCGTs with carbon capture and stuff like that. So there are a number of options, and there are a lot of technologies with different technology readiness levels, so the TRL level, which dictates where it is in the maturation state. At Shell, of course, we are also considerate of the energy transition, but Shell looks at it from the point of view of what we need to do today and also how we need to be ready for tomorrow, right? So the aspect of time in the whole energy transition is very important, because you can't think of a solution, your North Star, let's say, of 2070 for India or 2050 for Shell itself, and say, this is the bottom line I want to reach no matter what. Because the no matter what doesn't work, because the energy requirements for today need to be met, and then those need to be sustainably transitioned to the requirements for tomorrow. The aspect of time is important, and that's why I'm going to advocate for what we are calling a systems modeling approach, right? It's basically a systems engineering or a systems thinking approach, and by that I mean a holistic approach where you're not looking at your particular steam demand or energy demand just from a point of view of that particular equipment or that particular part of the plant, but look beyond that. Look beyond that, because there's so many interdependencies that affect what you decide. If you decide to replace, for example, a gas turbine in the LNG plant for compressing your gas in order to make it into a liquid form too easy to transport, you can't just look at GT as an equipment versus e-drive as an equipment, electric drive as an equipment. You need to look at how does it affect the maintenance of rest of my plant, how does it affect my turn down, and then you need to decide whether, based on the reliability and production estimates, it is definitely what you need to do. Because what we definitely don't want to do in the energy transition is to have take our steps back multiple times, because that's just going to slow our progress. So using the three examples, I'm going to show you how this methodology works. And like I mentioned, it's a systems thinking approach where you start to think of not just one aspect of the problem, but the whole of it together with as much dependencies as you find relevant. And then you add the computational advantage to it. You add computational science or modeling, which is the power that gives you the capability to model many permutations and combinations of the alternatives that you have. For example, you might want to think of, can I replace my fuel? Can I replace it from natural gas to maybe electricity directly? At the same time, what the equipment might cost, and what's the reliability of that equipment like, what's the maintenance cycle of that equipment like, and all of those things combined together, the alternatives, what's the pathway that you should choose? Because it's clearly not a straightforward road, right? So here on the slide, you see different stages of it. Of course, we know the scope and purpose. That might differ from time to time as well. For example, in 2025, based on regulatory requirements, you might have different consideration of what's the blended mix of your final product as compared to maybe in 2050 or 2070. You need to understand the baseline, because what are we optimizing against today, right? We want to be better than how we are performing today. And then, like I mentioned, the interdependency, and not only in terms of the technical details of it, that how does one part of the plant interact with the rest of it, but also in terms of the outer ecosystem. Because more and more so, the cost effectiveness of energy transition solutions is dictated by what is the incentive. Whether there is a customer at the end of the day who is willing to pay you extra for the decarb technologies that you implement on your site, and at the same time is the government providing enough of an ecosystem for you to take that risk. Decarb levers. By decarbonization levers, we mean what are your alternatives? Firstly, can you optimize your efficiency itself? So that's, of course, you reduce your energy demand as such. And then on top of it, what are the alternatives? Different fuel types, different sources of electricity, combinations, and stuff like that. So laundry list of things, and the more you have, and we are going to have more and more. Like we're hearing about more and more technologies being developed and matured. So you're going to have more and more options, and which is a good thing as long as you can make sense of it from a holistic point of view. And finally, the cost benefit analysis. So I'd like you to focus on the graph on the right end, right? It has a cost of production on the x-axis and the emission on the y-axis. And the star basically is where you would ideally want to be. Lowest emissions and lowest cost of production. But in reality, the solution exists in clusters, right? Maybe you're already at high emissions and low cost of production. You optimize your system that way, and slowly you want to maybe move to the lower circle towards the right, where you end up paying something in order to reduce your cost of emission. So how is your trajectory through these different clusters is what a decarb roadmap or a net zero roadmap would tell you. Okay. Yeah. And like I said, it is a temporal problem. You can't just say this is the snapshot in time and this is going to be my reality forever. So that's why what I'm trying to say is that the graph that we just discussed, cost of production and the emissions, that you need to develop based on your current understanding for multiple years to come. And what is the line there called the Pareto front is basically your minimum cost and increase of your UTC or cost of production and the maximum advantage you can take in terms of emission. And each dot, mind you, here is one permutation and combination that you can take up for your whole plant or multiple plants altogether. And the idea is finally to have something like this, where you can suggest different sensitivities for the roadmaps that you generate over time. And of course, this reality would keep changing, but once you have a robust representation of the system you're looking at, then you can easily run, like actually in seconds, different permutations and combinations to run through this. The first example I'd like to share with you, and my apologies, I can't share the data with you, but I'll share the conclusions from this study. So like I mentioned, in terms of going towards net zero, LNG business for Shell is very, very important. And like you saw in the first couple of slides, we are talking about the need for today, and for that, LNG is definitely one of the most important things. So one of the projects that we worked on as P&T support to Shell assets was that can we replace the GT drive with the E drive? So GT drive, by GT drive I mean gas turbine driven compression cycle, the refrigeration cycle for LNG, because you need to compress the natural gas in the liquefied form to allow effective, cost-efficient transport. So currently, it's the GT drives that are used, and on an equipment-by-equipment basis, I mean, if even by a simple Google search, you'll know E-drive, hands down, is as an equipment definitely better than GT drive. What an OEM would tell you is the GT drive has a given maintenance, and E-drive requires lower maintenance. Lower time for what is called mean time to repair. As soon as you have a failure, how much time is lost from your production in order to repair that? That is much lower for E-drive as compared to GT drive. So if you just look at that data, you'd be like, oh, all the GT drives in the world should be replaced by E-drives. There's no question about it. And that, green electricity, you're done with your decarbonization for the refrigeration cycle in LNG. But the moment you start to look at the interdependency, you see, okay, my GT drive is connected to something else in the plant. It is part of the gas value chain for LNG that starts from taking the gas out from the crust to really delivering it to a customer. So even from an LNG asset point of view, once you make the interdependency and the interface diagram, and we ran those scenarios using Monte Carlo simulations to test the reliability of the GT drive as opposed to the E drive as a system. So how much is your production at the end of the day affected by changing your drive?
Good morning, ladies and gentlemen. We welcome you to third
Sorry.
edition of IEW 2025. The show timings for today are from 10 a.m. to 6 p.m. All the visitors, exhibitors, and delegates are required to wear their badges at all times. Children below 18 years will not be allowed inside the hall. Please take care of your belongings. Thank you.
Thank you. I hope everybody here is more than 18 years of age, so good to go, I guess. Yeah, so what I was trying to say is that the moment you add all the interdependency and conduct a system level reliability and roadmap analysis, what we came across was two things. First, the reliability of the system level reliability of an LNG plant the moment you add an E drive and replace the GT drive with it, actually is poorer than the GT drive itself. The second thing that we found out is that there is a climatic dependence on the GT drive production, which is not the case with E-drive because your power is coming from an electric input. So that with that, you can compensate for the reduced reliability and then compete with the GT drive. And that depends a lot on which location you're talking about. For example, in Oman, the climatic conditions vary a lot and it's not as cool as, say, in Canada. So GTs perform poorer in Oman as compared to in Canada. And then E-drive, maybe for LNG assets in Oman, would be much more cost effective and practical as compared to in Canada. So every result, every decision in the roadmap that you make would be objective, but it would be location dependent and the regulatory requirements dependent. So what this process, this system modeling approach or the energy system modeling approach provides you is a very robust method to make informed decision, because nobody has the crystal ball, so you can't do that, but you can at least be confident in your decision when you make them. The next example I'd like to share. Okay. Can you change to the next slide? Yeah, so this is like direct electrification solution, and there are multiple solutions that Shell is of course looking at, from direct consumption like renewable generation itself, and maybe with the carbon capture technologies with their traditional ways of power generation. One thing in terms of heat integration is thermal energy storage, and it is a very attractive proposition. So similar to batteries for electricity, you have what is called a thermal energy storage for heat demand. With intermittent supply of power, either from solar or wind, or even if you're connected to grid, you might want to absorb that electricity intermittently because the electricity price fluctuates more or less on an hourly basis even from grid. So you want to make sure that you're competitive with, say, natural gas boiler or another kind of storage. So you want to absorb it intermittently and still provide a constant steam demand that you want to meet. So these kind of technologies, which are in between, say, technology maturation and technology deployment, a company would also want to know whether I want to invest in this particular technology. And then the moment you say whether this technology, if the TRL level improves, has a place in my decarb pathway or roadmap, then you have a stronger business case to justify the investment that you make in it. Because if you spend too much money and time in developing one technology, that means you're putting off some options from the table because you don't have enormous amount of resources and time. What Shell is offering is what is called a fully integrated thermal energy solution. We're trying to utilize it for our own assets. One of the deployment happened last year with more than 1 year of operation already, where we're converting intermittent electricity availability into constant steam demand that we meet by conversion of it into heat form. Lastly, this is an example with the hard-to-abate sector, actually aluminum industry. And the graph that you see on the right bottom is actually the dots that you see. Each of these are one simulation with different permutations and combinations. And there you can see again the connecting back to what we started with. Basically you choose the different points that you want in your process. Yeah. Okay. I hope I've convinced you to take this method a bit more seriously and think a bit more holistically, and if you have any questions from us, we'd be more than happy to answer afterwards. I would like to acknowledge all the people who worked over the years on this who could not be here today, but definitely their contribution was extremely valuable. Thank you so much.
Yeah, thank you, Abhiti. Wonderful presentation on industry decarbonization. Now I would like to invite Dr. Tarun Sharma. So he'll be sharing a presentation on organizing modeling capabilities to support sustainability transition of India's power sector. So over to you, Dr. Tarun.
Thank you, Chair. And first of all, apologies for being a little late. I planned to be here by 9:30, but the traffic just got the better of it. So the title of my presentation is a little esoteric, but I hope by the end of the presentation we have a fair grasp of what is it that I'm talking about. So the theme of the IEW this year is reimagining the future of energy in India for the world. So what is it that we're talking about? Energy in India, recent snapshot is what you see on the screen. So it's a large network of interconnected supply chains, all interacting to provision energy, energy being a good thing required for human development or GDP and lots of good things. But associated with it, then we know the externality of climate, and the other speakers have spoken before me, so I've also skipped the slides on the carbon budget, how much we have, and the big picture of, say, planning for a net zero by which year, when. But the key points here, so when we're trying to reimagine this, say in the year 2050, so energy sector we know is characterized by, say, capital intensive investments. So investments in assets which have large lives, longer lives. Say how it might look like in the future. That's the key question. And say we have propositions, a lot of which the speakers before me have also spoken about. So propositions for biomass, for hydrogen, for say the relative roles of, say, solar, wind, storage, carbon capture. So they all do not exist in silos. They're going to be put in a system where they're going to be interacting with each other. And you would want to be very careful about when making those investments, because again, as the previous speaker mentioned, we don't want to be taking steps back. It's simply the risk of say, stranding and other such things is large. Propositions are plenty at different levels of readiness level, meaning we have less confidence in that if they are actually going to be available at the cost, which probably is projected in the future, or if they're actually going to work as per the expectation. So essentially, this is the space where we have to work and where we have to think about reimagining the future, taking into account all these interdependencies, all this scarcity of information about different technological propositions about business models and whatnot. So how do we go about doing this? So that's the perspective which I'm taking. So to be able to sort of develop a technology roadmap, a vision for the entire system, accounting for all these various technologies and how they are interconnected, and at a fine temporal resolution, because renewable energy, as we know, varies from hour to hour, and at the same time, then you want to also be able to account for, say, investments which last 30 years. So, and the assets are spread over large geography. So all these things combined together is what is the task at hand. So and how do we go about it? So we map the entire energy system, all the interconnections, and let it play out and simulate its operation. And more specifically, so electrification is one of the dominant pathways in the net zero scenario. So we understand that electrifying lots of demand for energy and then provisioning that electricity from renewable energy, that's sort of one of the dominant pathways. So I'll restrict myself to the work which we're doing on electricity per se, while alluding simultaneously to say how things get done when you're trying to develop a vision for the whole energy system. Again, we know that the demand for flexibility in electricity is increasing faster than the demand. So what that means is we need the resources, say conventional thermal power plants, to be we need to be able to flex them. The requirement for the flexibility is actually bigger. If you actually look at the data, is higher than the rate at which the actual demand is increasing. And so renewable energy is sort of one of the main propositions, coupled with storage, coupled with say possibility of electrifying, say, maybe mobility or other hard-to-abate cement, steel, and so on. And then we have simultaneously, say, we have a Vision 2070 net zero, and we also have a Vision 2047 Viksit Bharat. So lots of competing interests. So do we have enough land? All that. So these are all considerations which one would want to be able to account for in their modeling framework. So how best to organize this kind of modeling, especially when it's going to be used to inform lots of this technology road mapping, which in turn is going to be responsible for setting targets. Because again, I think a recurring demand which you will hear is creation of demand mandate. But demand mandate, how do you decide that? Demand mandate for which set of technologies, especially when they're competing with each other? So the proposition is to be able to do this kind of modeling in an open source framework, of which there are examples elsewhere, so that the task of arriving at a consensus, consensus among all the stakeholders becomes relatively easy. So that's the key proposition, and towards this direction, we have done some projects, developed some tools, and did some analysis, published some work, which all is available with all the data. So that is basically what the main thesis of my presentation today is. Now, so I showed you the snapshot from a recent year in the Sankey diagram, where we could see all the flows from primary resource all the way to the end use. So how did we get here? So this is again from the NITI Aayog's dashboard. So we can see how the investments in, say, electricity generation side has been happening on the coal, oil, gas, wind. And on the extreme right, we see their plant load factors. And we know that is a very important consideration. And especially with more solar and wind coming into the picture, there's already worry about, say, reducing your stable load, minimum stable load at which you can operate, or maybe even run plants in, say, 2 cycles. So you shut them off in the morning, turn them off on again in the evening, but then, and the risk of stranding and whatnot. And of course, I know when I speak, more coal assets are being built just because you're not able to keep up with the demand at which it's rising. So this just where we have gotten about. And this is sort of an illustration of one of the important phenomena which pans out in the system for electricity. So especially, so I think it's a progress from camel to duck curve, and maybe you've seen it before. But the idea essentially being that, say again, this the data is little, I think 1 year old. So you have, say, a peak demand of 193 gigawatts, and if you have roughly, say, 100 gigawatts of solar, so in the day, the demand which the conventional system sees is actually around 100 gigawatts. So we have a conventional portfolio of roughly 210 gigawatts. So if you're running all of it at, say, 55%, so that's probably the limit up to which you can bring them down. And beyond that, either you have to turn them off, and that's a big thing, because that's a big deal, because then you incur the cost of startup, and you also lose on the life of the asset. So how does that work out? Which plants should be doing the cycling? So say this is one of the important dynamics which you would want to be able to capture. And this is not just capturing it for the sake of capturing, but then it has implications for, say, regulatory processes of how you're getting rewarded, or for shortening of your asset, or for incurring additional cost on startups and things like that. And also, say, if we assume, more renewable into the picture. So the current system only has bandwidth for absorbing 29 or 30 gigawatts of solar more, beyond which you'll have to start thinking about serious shutdown during the day. Other proposition, storage, maybe yes, maybe no. Other proposition, electrification of transport, maybe yes, maybe no. So you see how these things are interacting with each other, and are sort of, these are all high stakes decisions. So the premise is essentially that you should be able to model all these things, analyze all these things, and then project the system in a public way, so as to be able to get on the same page all the stakeholders. And this is just that going forward, it's only going to get more complicated. So we already have targets for 500 gigawatts of solar, say for 2030, and we still don't have a very good idea of, say, what our detailed strategy is for, say, 2070 or thereabouts. So, which we have already committed for by 2070. So within my group, so we essentially work with TIMES. It's a suite of modeling from International Energy Agency Energy Technology Systems Analysis Program. So we have a workflow on this. Energy RT and Switch are two open source modeling tools. Now, who's doing this work? Say, if you read CEA reports, or if you look at NITI Aayog reports, so at the back end, some similar tools are being used. And then also have to think about data pipelines, because again, you're going to need a lot of data to be able to map the entire system, and then also being able to take into account the variability of solar, wind, which varies across regions. So it's a big enterprise. So mostly we focus on this, and then this is just one snapshot. Again, a work in progress, but say 2070, what the relative shares could be under a net zero thing. So India energy security scenarios, 2047, maybe 5,000 terawatt hours of electricity, but net zero 20, maybe it's double that. So again, we are sort of able to contribute to the technology road mapping or developing these long-term visions through modeling platforms, modeling workflows like these. And this is another snapshot of, say, this work is open source, and this is essentially the thesis that if we maybe go down this road, and it's comparable to, say, the practice in Europe or USA, so maybe we are better off, we're able to agree on things faster, and then, so here, it's a little busy slide. So essentially, on the, so the different blocks are, say, 2020, 2023, 2030, all the way till 2050. And say, on the y-axis, it's hour of the day. On the x-axis, within each block is the day from day 1 to day 365 in that year. So we actually model entire year operation at an hourly resolution, and say, we can see then, for instance, if you look third or fourth from top, hydro, for instance. So we already can see that the seasonal pattern in the availability of hydro, on how that impacts, say, the other resource mix, and what that least cost resource mix or capacity mix should be in the first place. What is the role of solar? What is the capacity of wind? What is the capacity of, say, all the other assets? So we are able to do such kind of analysis, look at, say, dispatch patterns, say, in a lot of detail, in a nuanced level. In a particular location, say, we have one asset with CUF of, say, 20, another 18, 19. So how are they dispatching? When are they dispatching? So you're able to look at that, the same slide again. So IDEA is an initiative. It was started by Professor Balachandra from IISc Bangalore, and Professor Joyshri Roy, who is currently at AIT. And IIT Roorkee is sort of one of the active members in that consortium. So over the last 3-4 years, we've been able to build tools, collate a lot of data, and all with the open source tools. Say, those of you who are familiar, maybe we use R, we use GAMS, which is proprietary, but we also use, say, Julia, Jump, Pyomo, and all of it open source, all of it on GitHub, and anybody can look up. So IDEA is essentially standing for Indian zero carbon scenarios. Yeah, so this is what we have been up to in the last few years. And say, how is it different from other efforts? So you might ask, who else is doing this? So I think you know the answer. And every time you see a report, you should certainly ask, where is the data coming from, and what is the analysis based on? Does it have any biases or things like that? So in our effort, we use open source modeling tools and data. We strive for transparency with neat documentation. And essentially trying to build a community around the effort, which allows for, say, modeling teams in companies or maybe academic institutions to build more scenarios, analyze the assumptions more critically, and maybe get data on something which is interesting, and then fit it within the model, and then look at say, how it pans out. So for a typical modeling team, again, the typical decisions are when they set out on a modeling enterprise, trying to develop scenarios. So which selection of language? Again, Julia, Jump, GAMS, AMPL, those are the possible candidates. Solvers, Gurobi, Cplex, or there are some open source ones, GLPK. And again, data, what level of data, granularity of data is available, where all it's coming from, which all sources it's available, say for India. And again, there are some sources in this space. And then how easily, because the output itself is gigantic, it's massive. So how well we are able to handle generation of, say, multiple scenarios and then be able to visualize the results. So within Energy RT, that is what IDEA is currently based on. So the script is written in R. It is the underlying model generator is, and I think slides are there, so there's a lot of detail in there, and I think the slides would be available, so you can look it up. So it's just trying to pan out, say, how, say, a new modeling team setting out on taking a modeling enterprise, what all things they might consider, what all decisions might they take, because that's the trajectory for me. So I joined at IIT Roorkee 4 years back, trying to set up a modeling group, and sort of these are the choices which we've ended up making in developing this capability for doing modeling and doing modeling analysis. Okay, so I'll, for the paucity of time, I'll not go into the detail. So this is essentially what all we have been able to achieve in the last 3-4 years. So we've done a bunch of workshops, offsite event, where we had again people from Niti Aayog and CEA, and made contributions and presentations at lots of different places. And the paper is recently out. It just came out recently, so it uses the open source stack. And I think that's my time. And I think I'll leave you at this slide. So if you're able to sort of do this modeling work, this exercise of, say, creating visions, which then sort of feed into the roadmaps. I think if you do it in a better fashion, so it's a pathway for unlocking, say, opportunities faster. So to be able to settle the contentious issues, because it's a very contested space, right? We see that, say, in all the presentations, because everybody has propositions, all interesting ones, but they're going to be competing in an interconnected system. So that's my time. Thank you so much. Yeah, so that's the team which works with me. Thank you.
Yeah, thank you. Thank you so much, Dr. Tarun. Wonderful presentation. So I think we had good discussion on net zero, vision, and pathways. So all the presentations will be shared by organizers. So feel free, to reach out after the session to each and individual if anyone is interested to. So I'm now just going to conclude the session. Thank you so much, everyone, for your time. Yeah, thank you.